Hello, and welcome to another one of our online lecture videos. Here we're going to take a look at second-order systems and mechanical applications. We're going to be talking about eigenvalues and eigenvectors again in this section, but now with second-order systems. So the following problems that we're going to see deal with the mass and spring system here, which we'll go ahead and draw. So, say we have a wall here, another wall here, and what we're going to have this time is we're going to have two masses. You've been asking for it, we finally got it. Two masses. So mass m sub 1 and mass m sub 2, which means we get three springs. So a spring connecting this wall on the left to mass 1, though it's without a loss of generality. A spring connecting mass 1 and mass 2. And then a spring connecting mass 2 with the other wall, the right wall in this case, though it is sort of arbitrary. And spring 1 has spring constant K1. Spring 2 has spring constant K2, and spring 3 has spring constant K3. Now, if we take a look at this system that we have and we think about the equilibrium positions of mass 1 and mass 2, and we're not going to show this because there's actually a lot of cases, though maybe this is something that the TAs would like to do in the recitation. Otherwise, I'll just talk about it generically now, that no matter how we sort of alter the system, meaning if we pull mass 1 back or push it forward, then no doubt certain springs are going to expand or stretch or compress, and they're going to want to return back to some equilibrium state. If we are to take a look at all possible scenarios, what can we do with mass 1, what can we do with mass 2, what can we do with both of them, then every single one of those scenarios actually gives us the same system, which is very interesting. So maybe that's even something worth checking out on your own, is try to think what happens if mass 2 stays and I sort of pull mass 1 back to the left. How is that going to affect what's happening with my system? Or you could think about, well, what if I bring mass 1 over to this side, etc., etc., or what if I bring both of them in this direction? It should always result in the same system here, where we have mass 1 times x1 double prime is equal to negative parentheses k1 plus k2 times x sub 1 plus k2 times x sub 2. And then we have mass 2 times x2 double prime is equal to k2 times x sub 1 minus parentheses k2 plus k3 times x sub 2. And we get the following stiffness matrix. So I want to be clear here with the stiffness matrix, capital K, that we really need, in order for this to truly be the stiffness matrix, we need that mass m1 and mass m2 both carry values of 1. So if I wanted to be a bit of a stickler here about this, I would say, well, sort of push up my glasses, well, I'd say really what we should have is this negative k1 plus k2 divided by m1, and then k2 divided by m1, so dividing this first row by m1, and then second row we're going to divide by m2, so k2 divided by m2, and then negative quantity k2 plus k3 divided by m2. And so this is perfectly fine, but that's sort of saying that masses m1 and m2 both carry values of 1. Otherwise, we would have to make sure we divide by it. I think it's better to almost think about this system represented above, and just if m1 and m2 are values that are not equal to 1, divide them through, is sort of the idea. So here we have our stiffness matrix that we can work with. We're going to be focusing on two natural frequencies of the system, and we're going to describe its two natural modes of oscillation once we build the solution for the second order system. And let's talk about sort of the idea or the motivation behind that now. So we have this nice theorem. Let me read through the theorem. Second order homogeneous linear systems. If the n by n matrix capital A has distinct eigenvalues, and here I'm just calling them negative omega sub 1 squared, negative omega sub 2 squared, so on and so forth, till we get to the last one, negative omega sub n squared, and associated real eigenvectors, v sub 1, v sub 2, so on and so forth to v sub n, then a general solution of x double prime equals ax is given by, and here essentially we just keep adding. It's going to be coefficients times cosine plus coefficients times sine times respective eigenvectors. And we'll show how to build this. I don't think we really have to think about capital sigma notation, since in a lot of cases we're just going to see maybe two of these. With arbitrary constants. Now, there is a special case. Let's say we have a non-repeated zero eigenvalue, lambda sub 0, with associated eigenvector v sub 0, then the solution, x sub 0 at t, is this a plus bt times vector v, and this is the corresponding part of the general solution. And there's a remark that we're making here that I think is very well worded, but a bit sort of over the top in terms of how it presents it. It says the non-zero vector v is an eigenvector corresponding to eigenvalue 0, provided that a times v is the 0 vector. If x at t is equal to a plus bt quantity times that eigenvector, then x prime is equal to 0 times the eigenvector, which is equal to a plus bt times the 0 vector, which is true, which is equal to a plus bt times a times the vector v, which is equal to a times x. And I want to try to sort of go through and make a little bit better sense of that in what I think is a more reasonable way to approach it. But let me start by talking about some of this information up here. So we got second order systems, we got cosines and sines. Where does that come from? Well, the idea is that we have our second order system x double prime equals ax. And just imagine, forget about whatever notation we said earlier, just imagine that x is of the form, and let's go sort of very basic here, e to the alpha t. If I differentiate this to get x prime, and we are going to want to include eigenvectors with this when all is said and done, but for now let's just think about a generic exponential function. We know we should have eigenvectors and coefficients playing a role in the solution as well. But if I differentiate this with chain rule, I get alpha e to the alpha t. And if I differentiate again, well, now I'm going to have an alpha squared times e to the alpha t. But I want you to notice then that in the second order derivative, that x double prime is equal to alpha squared times e to the alpha t is what we said was x. So alpha squared times x. So this is the relationship that I wind up getting if I'm still using exponential functions to try to generate a solution. Now in that case, since x double prime is equal to ax, and x double prime is equal to some number alpha squared times x, it follows that a times x is equal to alpha squared times x. And this is an eigenvalue eigenvector system, right? Remember ax equals lambda x. This is exactly reminiscent of that. What I'm about to say next, I think, gets people a little bit upset with the content. So what I want to say next is that alpha squared is the eigenvalue, but alpha squared can, and I'll say and will, because we're going to see that, we're going to observe it, and will be negative. Don't think of it so much as something squared. In fact, when we go to look at some problems in the section, we're not going to be generating it in this direction. That would mean that we already know what the solution is, and we're differentiating twice over. That's not the case. We're actually going to start here at the end, and we're going to be starting with, hopefully, an eigenvalue eigenvector system, and then we're going to work backwards to try to build our solution. So what's going to be interesting to notice is that the eigenvalue, and forget that I'm calling it alpha squared, just think of it as some number, the eigenvalue as a number, can and will be negative. So I think it's almost better to maybe give it a different name. So instead of calling it alpha squared, I'm going to call it negative beta, just so that we can think about it as being something that's negative. So then in that case, if that's what my eigenvalue is, in order to build back my solution for x, I need to know what alpha is, not alpha squared. So in order to find alpha, I have to take square roots of each side. So we see then that alpha is equal to plus or minus the square root of this negative number. I'm calling it negative beta, but call it whatever you'd like. And here we can really think of this as being plus or minus square root of beta times I, which now we're thinking about this as something that's pure imaginary. So my e to the alpha t is really going to be e to this plus or minus square root of beta times I. And we know what that's going to look like from our characteristic equation. This means we're going to get c sub 1 cosine of square root of beta times t plus c sub 2 times sine of square root of beta times t. And since we're talking about eigenvalues, there needs to be some mention of eigenvector. So then I am going to have to multiply this by some associated eigenvector and build solutions in this way. But it is going to be sort of strange, so don't try to think of it in the way that I've generated this result sort of working forwards. Rather, we're going to be working backwards to try to uncover what our solution should look like. But I want to just mention now, we are going to have eigenvalues, so that's good. We are going to definitely have eigenvectors, so that's great. But the eigenvalues are actually going to be negative. And in order to work back from the eigenvalues to building the solution, that means we are going to have to take the square root of something that's negative, which is going to give us something pure imaginary, which is going to generate cosines and sines. Not all the time, but a lot of the time. That's the situation that we're going to be looking at in this case. So that's a bit of what I wanted to say there. Let's talk about this interesting wording here. So it's saying, if I happen to have a 0 eigenvalue, and think of it sort of as a typical eigenvalue system, ax equals lambda x, though maybe we shouldn't necessarily use lambda anymore. If this eigenvalue, just think of it as ax equals eigenvalue times x, if this eigenvalue is 0, then we have ax equals 0 times x, which is going to give me the 0 vector. So ax is equal to the 0 vector then. But we also know from our system that x double prime is equal to ax. So it follows from this that x double prime is equal to the 0 vector. Well, if I want to figure out what x is, I can just think about sort of integrating twice over with respect to t. So if x double prime is the 0 vector, then x prime is going to be some constant, and let me call that constant little b. And if I integrate again with respect to t, then x is going to be that constant little b times t plus a new constant a. So it builds back this solution for x. Now, of course, we don't just get the solution because we're talking about eigenvalues. There is a discussion on eigenvectors as well. So we're saying that x, our function of t, is going to be this linear function, a plus bt, times some eigenvector. And let me just call that v. Now, I can show in the other direction if I really want to, that this implies that the second order derivative is going to give me 0, and here really meaning the 0 vector. But we would just look at this and say, okay, the derivative of the constant is 0, derivative of bt gives me b, and then I differentiate once more, so now the derivative of b gives me 0 anyways. So this is going to give me 0, but it's also true that x double prime, if this is a solution, which we're saying it is, should be equal to a times x, which should be equal to a times, and what we said x was, well, it's this a plus bt times eigenvector v. So if x double prime is supposed to be 0, the 0 vector, but if x double prime is also a times this little a plus bt times eigenvector v, then I know that these two things should be equal. So we'd say, well then, make this look more like an x, then we know that a times little a plus bt times eigenvector v is equal to the 0 vector. But I have to be careful with what this implies. So my little a plus bt should not be 0. I'm not trying to say anything about what the constants little a and little b have to be, and I'm not trying to impose any restriction on t either. So what this means, that since this little a plus bt shouldn't be the thing that I'm calling out, I shouldn't be saying, well, this has to be 0. I'm not trying to make a restriction there. It means that a times v has to be 0, the 0 vector. And again, we're not saying that either one of these as factors is supposed to be 0, right? So that's not necessarily the case. In fact, the eigenvector should be non-trivial. We can certainly have a situation where a matrix times a vector produces the 0 vector, but that neither of those things happen to be the 0 matrix or the 0 vector. And you could think of some fun examples, right? Like you could, for example, I don't know, we'll do 1, -1, and then what if I have something like, do -3, -3, for example. So if I just do my row column rule, we'll see right away, that's going to give me -3 plus 3 gives me 0, and then, use your imagination. You go ahead and do it again. Here I could just do like 2, -2, seems reasonable. So 2 times -3 is -6 plus 6, so it's possible for me to generate this without making any restriction on either of these. But this is sort of what all of this information is saying. It says it in sort of a bit of a precise way that I think is a bit too funny for my taste, so I like to explain it a bit more organically. Let's take a look at what the situation's going to be. So let's take a look at some examples. We'll focus on our stiffness matrix here. Just as a reminder, if we have any values for M1 and M2 that are not 1, I have to divide them appropriately, but then otherwise we have this negative quantity K1 plus K2, and then K2, and then K2, and then negative quantity K2 plus K3. Let's see what's going to happen. What's the worst that could happen with our applications? Let me jot this down real quick so we have it to reference. Negative K1 plus K2, and then we had K2, and then down here we got K2, and we got negative K2 plus K3. And this first example is going to be very interesting. So right away, mass M1 and mass M2 carry values of 1, so I don't have to worry about dividing anything in my stiffness matrix, which is good. But I want you to notice that K1 and K3 are 0 and K2 is 2. So if I go back to that 2 mass 3 spring system, I have my left wall, my right wall, and we have our 2 masses, M1 and M2. Since K1 and K3 are 0, that means there are no springs there. So a way that we would think about this system is we'd say, really, this is a system where we have no walls. And just sort of these 2 masses connected together with a spring, but not connected to any walls. And no walls is kind of a harsh statement, because maybe there are walls, but the masses don't seem to know that there are walls, because they're not connected to them in any way, shape, or form. So that's kind of an interesting system to look at. Let's see what happens as a result of this. If I build that so-called stiffness matrix, we get negative K1 is 0 plus K2 is 2. K2 is 2, that's my first row. K2 is 2, and then negative K2 plus K3 is 2 plus 0. So this gives me the stiffness matrix, negative 2, 2. Second row is 2, negative 2. And just like we did before with our eigenvalue eigenvector systems, consider this matrix A, and then think about A minus lambda I. So that would subtract lambda on the main diagonal. And then I want the determinant of this. So determinant of A minus lambda I, well, that's going to be multiplying on the main diagonal, negative 2 minus lambda times negative 2 minus lambda, and then minus the product on the off diagonal is 2 times 2, and set that determinant equal to 0. And if I expand this out, negative lambda times negative lambda gives me positive lambda squared. We get positive 2 lambda, and then another positive 2 lambda gives me 4 lambda. Negative 2 times negative 2 gives me positive 4, and then I have minus 4 equals 0. So then I see 4 minus 4 is going to cancel, so this gives me lambda squared plus 4 lambda equals 0, which I can factor. Lambda times in parentheses lambda plus 4 equals 0. And from this, I get 2 eigenvalues. I get lambda equals 0, and I get lambda equals a negative number, as promised, as advertised. Lambda is negative 4. So 0 and negative 4. Okay, well, so now we can go ahead and try to build our solutions. So right now, we're still doing stuff like we did in the previous section when working with eigenvalues and eigenvectors. So right now I have my eigenvalues. I'm going to need now to build my eigenvectors. So let's start with lambda equals 0. We do a different color for this. Lambda equals 0. Feels like baby blue. Lambda equals 0. We're going to augment this. So let me clean this up a bit. If lambda is 0, then subtracting lambda has no effect, right? So I just get negative 2, 2, and then 2 minus 2, and then augmented with the 0 vector. And I want to try to reduce this. So here, notice that these rows are dependent. I can replace row 2, for example, with row 2 plus row 1. This gives me a row of all zeros at the bottom. I have this negative 2, 2 augmented with 0. And from this, I can build an equation. So think about this top row as an equation that's saying negative 2 times whatever you want to call it. We'll say a sub 1 plus 2 times a sub 2 equals 0. Or if I move this term over, that means 2a sub 2 is equal to 2a sub 1. And dividing both sides by 2, this means a sub 2 is equal to a sub 1. Now my vector that I'm trying to build in general should be a vector with entries a sub 1, a sub 2. And I know a relationship between them, that they're in fact equal. So there's a lot of different candidates for an eigenvector that you could choose. I would always say to pick the nicest looking ones. So you could pick 2, 2, you could pick 3, 3, you could pick negative 7, but I am going to pick 1, 1 is, I think, the best eigenvector in this case of this form. So don't get too crazy with it. Though you could get crazy with it. Born to be mild is the motto. So here I get the vector 1, 1. Remember, it's a non-trivial vector, so don't pick 0, but try to pick it so that it looks as nice as possible. Okay, not so bad. So we're going to hold on to this. We're going to build it into our solution in a second. But first, I want to work with the other eigenvalue. Now, something that I should do while working with these eigenvalues, or even sort of on the way, is to think about what the frequency should be. So like we were saying before, the eigenvalues that we're working with are really squares of what should be in the exponent of the exponential function. So let me sort of drift back to what I was talking about. I'm getting this eigenvalue. We said, well, it's something like alpha squared, but don't really think of it as something alpha squared. Think of it as whatever my eigenvalue is, to return to my solution, I have to be taking square roots of that. And here with 0, the square root isn't really very exciting. Square root of 0 is 0. And, we wouldn't necessarily even call it a frequency, so to speak. There's a special term that we're going to use. But for negative 4, now that's going to be something interesting. If I take the square root of negative 4, sort of plus or minus, then we're going to get this 2i business. And this is our frequency. Or really, we refer to the frequency as being 2. So with these eigenvalues, we can start thinking about if I square root, what's it going to look like? It's going to give me some frequency. I don't know what this gesture was. I talk with my hands a lot. I think I just said that I'm crazy. This crazy guy's talking about frequencies. Well, why? Because he loves differential equations. So of course, if that makes him crazy, then so be it. And he's speaking about himself in the third person too, and I think that's great. Anyways, let's get rocking and rolling with the eigenvalue and find our eigenvector for sure. So now we got to subtract negative 4 from the entries on that main diagonal. So in both cases, that's negative 2 minus negative 4. Negative 2 minus negative 4 is negative 2 plus 4, gives us 2. So we get the matrix 2, 2 augmented with 0, 2, 2 augmented with 0. And this looks like it's not even really trying that much. I can right away replace row 2 with row 2 minus row 1. Gives me a row of all zeros at the bottom. And I'm left with this top row, 2, 2 augmented with 0. And again, trying to build a relationship from this, we would say, okay, 2 times a sub 1 plus 2 times a sub 2 is equal to 0. Or it follows then that 2 times a sub 2 is equal to negative 2 times a sub 1, or furthermore dividing by 2 that a sub 2 is equal to negative a sub 1. So if I want to build a vector from this, a non-trivial vector, I would say, well, let me let a sub 1 be 1, for example, and a sub 2 is the opposite of that, so negative 1 in this case. And that would coincide with the eigenvalue of negative 4, but we also said that coincides with a frequency of 2. Is important to think about. Because now we're ready to build our solution, and I want to be thinking about these things. My first eigenvalue was 0, and we discussed that special topic when we have a 0 eigenvalue. Then we wind up building our solution, where is it? Into this form here, a plus bt times vector v. Now I'm not going to use a and b because I like using, c1 and c2 and things like that, but it's just the idea of unknown constant plus unknown coefficient times t times that eigenvector. And that's the case for where we have this eigenvalue of 0, which is what we saw first in our first example. So building our solution, we call x at t the solution. We're going to take that first eigenvector that we got, and that eigenvector was 1, 1. And since the eigenvalue was 0, this should be times c sub 1 plus c sub 2t. And then plus, now I want my second eigenvector. I want to talk about the other piece to my solution. The second eigenvector was 1, negative 1, times this other piece of the solution. Now be careful. Here we said lambda, our eigenvalue, is negative 4. That should be the square of what is in the exponent on base e. So if we think about building the function back, well, it should be e to this plus or minus square root of negative 4 times t. And remember, this is pure imaginary, so this builds sinusoidal functions. This is going to build cosine and sine, and the frequency then is going to be square root 4, which is 2, right? This, we said earlier, this is going to end up being something like square root 4 times I, or that's 2I. So this other piece, since the square root of 4 is 2, it's going to be c sub 3 cosine 2t plus c sub 4 sine 2t. But now what I can do is I can go ahead and expand this out and try to get my separate solution. So here, x at t, let's still work with vectors for a bit, and I'll get a big vector. For the top entries, it's 1 times c sub 1 plus c sub 2t, which is c sub 1 plus c sub 2t, plus, and then 1 times my cosine and sine, so then plus c sub 3 cosine 2t, plus c sub 4 sine of 2t. And then now for the bottom row, it's 1 times my linear function, which is c sub 1 plus c sub 2t, and then minus 1 times my sinusoidal function, so minus c sub 3 cosine 2t, and minus c sub 4 sine of 2t. And now we can extract the separate pieces. So we have top row, bottom row are going to be x sub 1 and x sub 2. So x sub 1 is going to be c sub 1 plus c sub 2t plus c sub 3 cosine 2t plus c sub 4 sine of 2t. And that's for x sub 1, the solution involving mass m sub 1. X sub 2 at t, the position function involving mass m2, is going to be this bottom row, which is c sub 1 plus c sub 2t minus c sub 3 cosine 2t minus c sub 4 sine of 2t. Now we want to talk about these in terms of natural modes. And so what we do is we compare the solutions on x sub 1 and x sub 2 for the like parts. So first, let's take a look at the first two terms for each. The solutions are in fact identical. So we'd say, and this is referring to what's happening with the frequency associated. So we'd say there's going to be a lot of writing. In the natural mode, and it's really referred to as a degenerate. I said there was a special word, the degenerate mode, with frequency. I'm going to put frequency in quotes because it's really not a frequency. Omega equals 0. We would say both masses, M1 and M2, move by translation without oscillation. And I want to come back and talk about why that's what we're seeing and how it ties into what we said even earlier. But while we're here, let's then talk about what's happening in this other natural mode. So this other natural mode does have a true frequency. That frequency was 2. I got cosine 2t, sine 2t, and then again. So we'd say in the natural mode, this is not degenerate, this is the good stuff. In the natural mode with frequency, I'll scooch down, with frequency omega equals 2, the masses move, and I want to describe the directions and the amplitude. So I'm really looking in front of cosine and sine. They have the same arguments, but I want you to notice that in front, they're exactly the same except opposite signs. Now, I don't know what C3 and C4 are, so I can't really comment on which one is going to wind up staying positive or staying negative, but I do know that they're opposite signs, which means that they're moving in opposite directions. So whichever one is moving in the positive direction, the other one's moving in the negative direction, and vice versa. So we would say in the natural mode with frequency omega equals 2, the masses move in opposite direction with equal amplitude. And we know equal amplitude because there's no distinguishing coefficients that are altered. We'd say, well, this is a +1, this is a -1. This is a +1, this is a -1. If there was, say, like a 3 in front of these ones up here, well, then there would be a different amplitude. So we're looking at a couple things. We're looking at comparing like parts. This is a special case with the degenerate mode and sort of the pseudo frequency at 0, which I want to go back and talk about in a second. But when we have cosines and sines, we're looking at a couple things. Is there any difference in the coefficients by magnitude? And is there any difference by sign? If there's a difference by sign, like here we have positive versus negative, that means opposite directions. So opposite directions. If there's a difference in magnitude, which this is not a great example of that because there isn't, if there's a difference in magnitude, that means a distinction in amplitude. So here we're saying for the linear pieces, we can compare, since, you know, trying to compare apples and apples and oranges and oranges. We say in the natural mode with the degenerate mode with frequency omega equals 0, both masses move by translation without oscillation. But then we do have a true natural mode with frequency omega equals 2, that the masses move in opposite directions with equal amplitude. So hopefully that information about the opposite direction equal amplitude makes sense. What's interesting though is this degenerate mode. So I say moves by translation without oscillation. Why is that? And this is sort of strange. We only see this when we have this eigenvalue of 0. Well, let's go back to what we said in the beginning of our example. Since K1 and K3 were 0, this is no walls to the system. So here we just have two masses connected with a spring. How can I think about that translation without oscillation? I like to think of a sort of an application of this. Let's say I have two masses connected by a spring, and I hold on to one of the masses, and I pull that other mass back, and well, then it's just going to move by translation without oscillating. It's sort of a funny example to think about. If you had two masses connected with a spring, you know, get a friend to hold one of the masses down, pull back the other one, and let her rip. And you're going to see that it's going to move by translation without oscillation. But then we have the other case where there is some oscillation that we can observe. at that natural mode of frequency 2. Let's take a look at another example. Now I want to be careful with this one because I'm noticing right away that mass 1 is 1, but mass 2 is 2. So when I go to build that stiffness matrix, I'm going to have to be careful. So I'd start by saying, okay, here I want negative parentheses K1 plus K2. 1 plus 2 gives me 3. And then K2 by itself is 2. And then for the second row, it's going to be K2 again, which is 2. And then negative K2 plus K3, which is negative 4. But since mass 1 is 1, I don't have to worry about the top row. But since mass 2 is 2, I actually have to divide these entries by that. And I could divide by mass 1. It's just not important because it's just dividing by 1. But I do want to notice right away, hey, mass 2 is not 1, it's 2. So that means row 2 gets divided by 2 to make sure that my stiffness matrix is correct. And so this just corrects it. So then I get negative 3, 2, and then we get positive 1, negative 2 for our matrix A. And then we look at A minus lambda I as a matrix. So here we're going to have negative 3 minus lambda, and then 2, and then 1, and then negative 2 minus lambda. And I want to look at the determinant of this matrix. All right. Determinant of A minus lambda I. That's going to give me negative 3 minus lambda times negative 2 minus lambda, and then minus 2 times 1 equals to 0. If I expand this out, negative lambda times negative lambda is positive lambda squared. I get 2 lambda plus 3 lambda gives me 5 lambda. Negative 3 times negative 2 is positive 6, and then minus 2. But then if I go ahead and collect my like terms, just the constants at the end, lambda squared plus 5 lambda plus 4 equals 0. And this will factor into lambda plus 1, lambda plus 4. So here we get eigenvalues of lambda equals negative 1, lambda equals negative 4. Remember, though, that these are actually squares of what should be in the exponents for our exponential functions. So these are actually going to behave as frequencies. And let's, for example, start with lambda equals negative 1. Lambda equals negative 1, the corresponding frequency here would be 1. So think about taking the square root of this, but the square root of the magnitude. So we could really say what we're saying for omega is the square root of the magnitude of lambda, if you want to think of it that way. I also like to think of it as, well, what happens when you get those pure imaginary terms in the exponent from the characteristic equation. But so for right now, the frequency comes into play when we're building our solution. For right now, though, I'm working with the eigenvalue. We like to do this in the baby blue. So let's get the baby blue. If lambda is negative 1, well, what is A minus lambda I? Negative 3 minus negative 1, that's negative 3 plus 1, gives me negative 2. And then 2 augmented with 0. And then we have 1. And then we have negative 2 minus negative 1, which is negative 2 plus 1, which is negative 1. So hopefully we can start to see, well, these rows are dependent, so I can eliminate whatever row I'd like. That doesn't really matter. I can get rid of row 1, for example, replace row 1 with row 1 plus 2 times row 2, an elementary row operation. Negative 2 plus 2 is 0, 2 plus negative 2 is 0, 0 plus 2 times 0 keeps 0 in the augmented entry. We're left with this row, 1, negative 1 augmented with 0. Think about this as an equation, though. What does this row represent as an equation? If you really love linear algebra, you know that I shouldn't leave this down here, but I'm letting my hair down today. This row 2 says A1 minus A2 equals 0, or that A1 is equal to A2, which if we work with eigenvectors a bit now, maybe we can already build that eigenvector. It's some vector of the form A1, A2, but A1 and A2 are equal, should be non-trivial vector. So are you thinking what I'm thinking? I'm thinking 1, 1. It's my favorite. So this is my eigenvector, and this was associated with an eigenvalue of -1 with a frequency omega of 1. So I'm actually ready to build this part of the solution, but I'll wait till I have all my pieces. Let's go to the pink now for lambda equals -4. Lambda equals -4, we can comment right away that our frequency then, if I take the square root of the magnitude of the eigenvalue, that's 2. So frequency is 2. We kind of saw this in the last example as well. Then I want to work with this eigenvalue, though, -4, to build my system. Already ready. Let's plug in -4. -3 minus -4 is -3 plus 4 gives me 1. And then 2 augmented with 0, and then we have 1 in the bottom row. And -2 minus -4, that's -2 plus 4, gives me 2. So I can see very directly that these rows are dependent. So I can remove one of the rows, say replace row 2 with row 2 minus row 1, gives me a row of all zeros. I'm left with this top row. And what is the top row saying as an equation? Well, it's saying a1 plus 2a2 is equal to 0, or that a1 is equal to -2 times a2. And I'm going to try to pick the nicest vector in this case. So I would say, well, let me pick, I don't know why I'm this way, but I always like a sub 1 to be positive. Does it have to be that way? No. But, you know, once you get to be as very old as I am, you can't really change anything about yourself. So I would say, let me pick a sub 2 in this case to be -1. So then a sub 1 is -2 times -1, which is +2. Why? Because I'm crazy. I need that first value to be positive or else I'm going to be upset all day. Don't even ask me about it. Lambda is -4. Frequency is 2. Now we are ready to build our solution. Now maybe let's color code it so we can see where the pieces are coming from. So x at t is equal to, let's start with the first piece we did in the baby blue. I want this eigenvector that I built, which was 1, 1. And then this gave me lambda is -1, which think about that as e to the plus or minus square root of -1t power. That's a complex, pure imaginary exponent. So then by Euler's identity, we're going to get sinusoidal functions. The sinusoidal functions are going to have a frequency of 1 in the argument. So that's going to be my parentheses c sub 1 cosine of 1t plus c sub 2 sine of 1t. And then I'm going to add to this. Now I'm ready for the other piece. I did that in the neon pink. We have this other eigenvector, 2 minus 1. And then for that, we had the eigenvalue -4, which corresponds to the frequency of 2. So that's going to be, in parentheses, c sub 3 cosine 2t plus c sub 4 sine of 2t. And this is my solution, building out those separate pieces. Now what we want to do from here is we want to build this into a full vector, for example, and then extract the separate pieces. So if I look at these upper values, here I'm multiplying 1 in, so that's c sub 1 cosine t plus c sub 2 sine t, but then for sine of t, I said it right, but I wrote something different. C sub 2 sine of t. But then for the other pieces, I'm multiplying this 2 in. Notice the 2 from the top of the vector. So plus 2 c sub 3 cosine 2t plus 2 c sub 4 sine 2t. And then now traveling along the bottom row. So now I'm going to have 1 times, so same thing essentially, c sub 1 cosine t plus c sub 2 sine of t. And then multiplying -1 in, we get minus c sub 3 cosine 2t minus c sub 4 sine of 2t. And we can extract these out as separate pieces. So top row is x sub 1. X sub 1 at t is c sub 1 cosine t plus c sub 2 sine of t plus 2 c sub 3 cosine 2t plus 2 c sub 4 sine of 2t. X sub 2, so the solution x sub 2 at t, right here in the bottom row, c sub 1 cosine t plus c sub 2 sine of t minus c sub 3 cosine 2t minus c sub 4 sine of 2t. Now I want to compare pieces and talk about the modes and what's happening at those frequencies. So we'll compare, so remember solution on x sub 1 and x sub 2 referring to mass m1 and m2 respectively. I can compare these first two terms together since they're both talking about the same types of sine and cosine. So we'll say in the natural mode with frequency omega equals 1, both masses, what do you think? Both masses move in the same direction, talking about direction and amplitude, in the same direction with equal amplitudes of oscillation. That one's not quite as exciting to talk about as what's happening in the other frequency. So I compare these pieces, and what do you think about this? Well, so my frequency was 2. So we'll say in the natural mode, sorry about my handwriting, but I think it's good enough. In the natural mode with frequency omega equals 2, the masses move. And what do you notice? I notice positive, positive, negative, negative. That means they're moving in opposite directions. So the masses move in opposite directions. But then what else can we say about amplitude? Well, generically, aside from the sign that's different, notice for mass 1, I have 2c3 and 2c4 for the amplitude, whereas for mass 2, I have c3 and c4. So think about that sort of as a ratio. What we would say is, with the amplitude of mass 1, twice that of mass 2. So in opposite directions, with the amplitude of oscillation of mass 1 twice that of mass 2. So that's how we're sort of comparing these. We're saying opposite directions because one is plus plus, the other is minus minus. Comparing amplitude, 2c3 to c3 and 2c4 to c4, thinking about magnitudes of coefficients, mass 1 has twice the amplitude of mass 2. So in the natural mode with frequency omega equals 2, the masses move in opposite directions with amplitude of oscillation of mass 1 twice that of mass 2. And let's take a look at one more example. Now I really think it'd be good for you to pause the video and try this one on your own. And I'll just drink some Gatorade that's been replaced with water. Did you finish the problem yet? Well, let's take a look at, hopefully you paused the video and went through the problem. Let's take a look at what we get. So here we have negative k1 plus k2, so that's 2 plus 1 gives me 3, so negative 3. And then k2 is 1, and then k2 is 1 again, and then negative k2 plus k3, so that's 1 plus 2, so negative 3 again. And since mass 1 and mass 2 are both 1, I don't have to worry about correcting this. But remember, we said earlier, I would have to divide row 1's entries by mass 1, and then I'd have to divide row 2's entries by mass 2, the values that we get for that. So this one's pretty quick to get the stiffness matrix, and then I want to look at A minus lambda I. So on the main diagonal, I get negative 3 minus lambda and negative 3 minus lambda. And the entries on the off diagonal stay preserved. And I want the determinant of A minus lambda I. Of course I do. I always want the determinant. That gives me, multiplying on the main diagonal, negative 3 minus lambda times negative 3 minus lambda, and then minus the product on the off diagonal, 1 times 1. Set that determinant equal to 0. Try to force those non-trivial solutions out from the invertible matrix theorem. If you're a fan of linear algebra, what? Let's multiply this out. Negative lambda times negative lambda is positive lambda squared. I get positive 3 lambda, and then another positive 3 lambda gives me 6 lambda. Negative 3 times negative 3 gives me positive 9, minus 1 gives me plus 8, equals 0. And this will factor. We get lambda plus 2, lambda plus 4. So we get eigenvalues, lambda equals negative 2 and lambda equals negative 4. Remember though, these are squares of what we should be putting into the exponent of the exponential function. So let's see if we can work with these accordingly. Let's start with lambda equals negative 2. So with lambda equals negative 2, that is the eigenvalue. However, the frequency is square root of 2. And if I work with this eigenvalue of negative 2, I should be able to get an eigenvector to coincide with this. So I get negative 3 minus negative 2, that's negative 3 plus 2, gives me negative 1. And then 1, and then 1, and then another negative 3 minus negative 2. So another negative 3 plus 2, so another negative 1. And I can eliminate row 2, for example. Replacing row 2 with row 2 plus row 1 gives me a row of all zeros. I'm left with row 1 to work with. And row 1 as an equation says negative a1 plus a2 is equal to 0, or that a1 is equal to a2. So my vector, which should have entries a1 and a2, I know that the entries should be equal. So without getting too crazy here, I'd say, hey, a good eigenvector would be 1, 1. And this corresponds to the eigenvalue, negative 2, but the frequency, square root of 2. Once you've worked with eigenvalues and eigenvectors enough, it starts to become a little bit quicker. The other eigenvalue, lambda equals negative 4, so let's see, what did you get for the eigenvector for this? Try to get those nice ones. This has a frequency of 2, square root of 4. Right, square root of the absolute value of the eigenvalue. And then if I use the eigenvalue, lambda equals negative 4, so always the eigenvalue at this point, the frequency comes into play when we build our solution. What are we going to get? Well, negative 3 minus negative 4 is negative 3 plus 4, gives me 1. So I get 1, 1, 1, 1. And I can eliminate row 2. Replacing with row 2 minus row 1 gives me a row of all zeros. I'm left with 1, 1 augmented with 0. And this says a1 plus a2 is equal to 0, or that a2 is equal to negative a1. So when I go to build this vector, it's going to have entries a1, a2. But then using this relationship to build the non-trivial vector, I'd say, well, let me let a1 be 1. Then a2 is the opposite of that, so negative 1. And this corresponded to the eigenvalue of negative 4, more importantly, corresponded to a frequency of 2. And now I'm ready to build my solution and to describe my solution. So here we have x at t is equal to, we'll do this piece by piece. So in the baby blue, we got an eigenvector 1, 1 times in parentheses, our frequency was square root 2. So that should be c sub 1 cosine square root 2t plus c sub 2 sine of square root 2t. I'm cutting it kind of close, but you can see those are square root 2's, hopefully. And then the purple, we got a vector 1, negative 1. And then here the frequency was 2, so we should have c sub 3 cosine 2t plus c sub 4 sine of 2t. And now I can build this out to the separate solutions. Instead of building that super vector first, let me just go right ahead to the separate solutions for x sub 1 at t and x sub 2 at t. I think at this point we can probably start to see where they're coming from and what they're going to be. So here, if I think about the top row, 1 times the stuff in the blue parentheses, we get c sub 1 cosine square root 2 times t plus c sub 2 sine square root 2 times t, and then plus, still traveling along the top entries, it's another 1 times the stuff in the purple parentheses, so that's c sub 3 cosine 2t plus c sub 4 sine of 2t. Now for the bottom entries, again, it's 1 times the stuff in the blue parentheses, so c sub 1 cosine square root 2t plus c sub 2 sine square root 2 times t, and then now negative 1 times the purple parentheses, so negative c sub 3 cosine 2t, negative c sub 4 sine of 2t. And now we can describe these one at a time. So if I'm looking here at the like arguments, we'd say, well, look at what's happening, nothing really too interesting, so let's describe it then. We would say in the natural mode with frequency omega equals square root 2, both masses move in the same direction, since they carry the same signs, not opposite signs, with equal amplitudes of oscillation. So I noticed that the coefficients are exactly the same sign, same magnitude. Okay, let's take a look at with the argument and frequency of 2. 2t is the argument. Let's say, well, I can compare these two across mass 1 and mass 2. And we can start by saying in the natural mode with frequency omega equals 2, in the natural mode with frequency omega equals 2, the masses move in, let's take a look. So here we have plus plus, minus minus, opposite directions. So the masses move in opposite directions. What about the magnitude of the coefficients? Other than that, the coefficients are the same. So just the flipping the sign, but otherwise it's C3, C3, C4, C4. So the signs are the same. We would say opposite directions with equal amplitudes of oscillation. So in the natural mode with frequency square root 2, same direction, same amplitude. In the natural mode with frequency 2, we have opposite direction, equal amplitude. And that is it for this section. Let me go ahead and put the homework in the homework jar. Please take a look at our homework on our online homework platform. Let me know if you have any questions on this. I'd love to talk more about this system. I got an extra page here in case I needed it for notes. Let me know if you like the 2 mass, 3 spring systems on our discussion board. But otherwise, remember to keep learning, to keep dreaming, and to always follow your heart. And I'll see you again soon.